So now let's begin discussing the Schrödinger equation for the hydrogen atom. In particular, we're going to look at the eigenvalue expression for it. So I'm going to write down the Hamiltonian, which will contain a kinetic energy term and a potential energy term. The kinetic energy will be associated, of course, with the motion of the electron around the nucleus, and the potential energy will have this Coulomb form of 1 over r times the product of the charges. So here we have, again, the kinetic energy for the single particle in 3 dimensions, and then we have the potential energy in the Coulomb form. But notice that I wrote a subscript called SPH. The reason is that these 3 dimensions are expressed in a radius and 2 angles theta and phi. And why is that? Due to the spherical symmetry of the hydrogen atom, it's much easier to think about it in these coordinates rather than in Cartesian coordinates. The price that we have to pay for this change of coordinates, it's a very complicated Laplacian. Let's look at it. So this is the Laplacian, or second derivative, in 3 dimensions. So of course, we're staring at a very complex expression, but luckily, you can probably identify at least a piece of it. The second part of it, we already saw before when we were discussing angular momentum in the previous lecture. In particular, we can rewrite it as the following. And then there's another piece that appears here, of course, as a function of r now. And then, of course, r appears here as a denominator as well. So, of course, this new coordinate r changes the form of the Laplacian, but this form here, again, reminds us of the angular momentum operator that we were discussing previously for the rigid rotor. So now, armed with this Laplacian, we can actually write again the eigenvalue expression, a second version for it, for the hydrogen atom. And here we go, the eigenvalue expression again. And now we can actually think about the energy contribution of these different terms of the Hamiltonian. Here we have all these p's that will correspond to the radial kinetic energy. Then we have the centrifugal force term that has to do with angular momentum. And of course, we have the Coulomb type potential energy. Armed with this, we're ready to solve this equation to find its eigenfunctions and expressions for their eigenvalues. You know what happens when I come in this t-shirt? Something has to be changed in the slide. How many of you, my hundreds of thousands of people watching me on the internet, have detected the thing that we need to change in this slide to make it all correct? Raise your hands. A few of you, I know, you're furious because you noticed there's a 2 missing in this slide. This term of the kinetic energy is 2 over r instead of 1 over r. Thanks to all of those that caught it, and if you didn't catch it, probably it didn't matter too much. So I had to put on my fancy jacket to talk about the Schrödinger equation again. Here is the eigenvalue equation for the Schrödinger equation that we saw in the previous slide in angular coordinates r, theta, and phi. And to make progress, I'm going to make an ansatz. I'm going to guess that there is a separation of variables in which the eigenfunctions phi of n will be written as a product of radial functions that depend on radius, and then angular functions that depend on theta and phi. Furthermore, these angular functions, I'm going to make an ansatz, will be the spherical harmonics because of the spherical symmetry of the electron cloud around our hydrogen atom. Okay? That will make the ansatz look like this. Furthermore, the radial part depends on quantum numbers n and l, and the angular part will depend on quantum numbers l and m. Therefore, the Sherwin quantum number, l, and the radial contains the information about n, and the angular contains the information about m. Okay, that's the structure. We'll see more about it, learn more about it during the entire course. And now let's see something else. Okay, how will the Schrödinger equation for the radial piece look like? Okay, so we're going to just concentrate on the solution for the radial piece because we already know from the previous lectures what the solution for the angular piece is. Everything that we know about the spherical harmonics will apply for the angular piece. But the radial piece is the first time we see this monster. Okay? And how is that equation coupled? You see, we share this quantum number L. And they're connected by this quantum number L because notice that we have the operator L squared here, whose eigenfunctions are the spherical harmonics. So when this operator L squared acts on a spherical harmonic, we know we're going to get back its eigenvalue L times L plus 1. And that will appear in the following radial equation. Okay, so a lot of it's going on. Here we have a radial piece that comes from this part of this eigenvalue equation and a lot of algebraic manipulation. Here we have the eigenvalue of the operator L squared over R squared. Okay, and we also have, as an eigenvalue for this equation, the energy depending on the quantum number n. Okay, so I put the quantum number n in red there to remind you, okay, that's the single quantum number that defines the energy of the hydrogen atom, for which we already have an energy expression. To remind you what it is, let's just write it down. Okay, so here we have the energy that depends inversely proportional with the reduced mass mu, the Bohr radius squared, times this quantum number n squared. And again, this is the quantum number n that appears here as the quantum number of this radial equation. Okay? So now let's remind you what is the Bohr radius. The Bohr radius is inversely proportional to the reduced mass and the charge squared. So now we understand what are all the constants that enter here as well, and we're ready to actually solve the differential equation that is stated here. Okay? This is the radial differential equation. That's a very arduous task that we're going to skip and just show you the solutions and get an intuition about them in the next few slides. So the radial eigenfunctions that satisfy this differential equation have basically three pieces. The first piece here in this square root is just a normalization constant that depends on the Bohr radius and the quantum numbers n and l. Here we have also an exponentially decaying piece, okay, that depends on r, as you can see here. And this is modulated by a family of special functions that we like to call the Laguerre polynomials. Okay? And we see here that the Laguerre polynomials depend on the quantum numbers n and l, and they have as an argument r over n times a0. In the next slide, we'll see how the energy has some degeneracies, because we notice that we have certain values of L that are allowed, but only a single energy for all of them that depends on n. Okay, so we learn about the degeneracy and how it plays along in the energy spectrum of the hydrogen atom. And then we will come back to how these eigenfunctions look like once we multiply these Laguerre polynomials times this exponentially decaying function.